Hey everybody, welcome back to Mr. A's Geometry course. Today we're going to be going over some miscellaneous information here in Unit 4 that involves transformations but not on the coordinate plane. Those things we're going to be reviewing are called lines of symmetry and angles of rotation. Let's get into it. First, we're going to discuss a line of symmetry, and this is the same thing as a line of reflection on a graph. It just exists when we're not on a graph. Right? For example, this figure here, that line, that dotted line that you may not have a good time seeing here, that line right there is a line of symmetry because I have mirror images on either side of it. Right? And hopefully you see the similarities between that and a line of reflection. This top vertex of the triangle is on the line of reflection. That's why the mirror image has a point on the same side. This bottom point right here appears to be equidistant on the other side. That makes this a line of reflection, which we can also say is a line of symmetry when we're not on a graph. A lot of figures that we deal with in geometry will have multiple lines of symmetry, right? Some of them are specific shapes that we learn about throughout the year. For example, a square with 4 congruent sides is going to have 4 different lines of symmetry. We can see the vertical one here, we see the horizontal one here, and then there's these 2 diagonal lines of symmetry. A rectangle, which does not have all 4 congruent sides, would have a different amount. We can see a vertical line and a horizontal line. Right, and then we have other shapes in geometry that we learn about that can also have lines of reflection, like the rhombus and so on. What's going to be most important for us is identifying the lines of symmetry on regular polygons. Okay, a regular polygon is a shape that has congruent sides. So all the sides on that shape are going to be the same exact length, just like a square, and congruent angles. So again, also like a square, all the angles are going to be the same amount of degrees. I meant to write angles there, my bad. So as an example, we have over here a regular polygon. Notice that all the angles have the same amount of arcs, telling me that the angles are congruent. All the sides have the same amount of dashes, telling me the sides are congruent. That makes this a regular pentagon, right? Just for clarity, right? Let me show you that this is a triangle. But if I say it's a 6, 8, 10 triangle, it's not regular triangle because the sides are not the same length. If I tell you that this triangle has all side lengths that are congruent to each other, let's say 8, 8, and 8, and all the angles are congruent to each other, that would make it a regular triangle. All the sides have to be the same length. All the angles have to be the same length. Regular polygons. For these regular polygons, it's very important to note, the amount of sides that the shape has, or the amount of vertices, and those will be the same number, right, the regular polygon has, will be equal to the amount of lines of symmetry that that polygon has. So again, the amount of sides or vertices, there should be the same number for a regular polygon, you will have that same amount of lines of symmetry for that regular polygon. For example, an equilateral triangle has 3 sides, 3 vertices. It will have 3 lines of symmetry. A square has 4 sides. It will have 4 lines of symmetry. A square is a regular quadrilateral because all the sides are congruent and all the angles are congruent. That fact will help us to answer questions like this. When we're asked how many lines of symmetry does a figure have? Well, we need to recognize this as a regular polygon. We can see all the angles have the same amount of arcs. They're congruent. All the sides have the same amount of dashes. They're congruent. That makes this a regular polygon. Once we know it's a regular polygon, all we need to do is count the number of sides. I got 1, 2, 3, 4, 5, 6 sides. Therefore, it will have 6 lines of symmetry. If you're concerned about where those lines would be, I'll show you. We'll have a vertical one right here. Then we'll also have lines that go through the vertices, like opposite vertices in the shape, like that. And then we have this one that goes through the middle of the sides here. We'll have this one that goes through those vertices. We'll have this one that goes through the middle of that side there. And then we'll have this one that goes through the vertices. All right, so you can see I have 3 green, 3 red, 6 lines of symmetry on this regular polygon. We will be expected to know the names of some kinds of shapes in geometry without having pictures of them. We need to know how many sides that shape has. For example, this question does not have a figure with it, just says how many lines of symmetry exist on a regular decagon. You'll be expected to know that a decagon has 10 sides. So if it's a regular decagon, it will have the same amount of lines of symmetry as it does sides. It would have 10 lines of symmetry. You also need to know a nonagon, an octagon, a heptagon, a hexagon, a pentagon. We need to know all those, the 10 sides and lower. We need to know the names of those figures. Another miscellaneous thing we need to know about here in this unit is rotational symmetry. So this is when a figure can be rotated 180 degrees or less and still look exactly the same as it did before you rotated it. Meaning that if it's fixed in the same position, you'll get the exact same figure. It'll appear that you haven't moved it at all. Okay, for example here, this triangle, if I were to take it and rotate it around its center point like this, a certain amount of degrees, it will eventually again look like the exact same triangle in the exact same position. I'll give you a more concrete example of that right now. We have a square here, right? And the angle of rotation on a square is 90 degrees, so it has rotational symmetry. If I can rotate this less than 180 and produce the same figure, our shape has rotational symmetry. And watch as I do this. I'm going to take this figure, notice the position that it's in right now. I'm going to rotate it exactly 90 degrees, and it's going to appear that the shape itself hasn't moved at all. Right? That's it. Rotating 90 degrees, it still looks exactly the same though as it did at the start. That is what rotational symmetry is. So that amount of degrees that we have to rotate for the shape to look exactly the same again is called an angle of rotation. So that's the amount of degrees required to, the word we're going to use here is map a figure onto itself. That's really what happened when I rotated that square 90 degrees. I just mapped it. It's just another fancy way of saying rotating it, where all the vertices lined up exactly where they were before I rotated, mapped onto itself. All right, and again, for the square, that was 90 degrees that I turned it. It's a quarter of a turn. For other figures, it'll be a different amount of degrees, and that's going to be the purpose here of what we're learning, is figuring out what that angle of rotation is for these shapes that have rotational symmetry. So to find our angle of rotation for any regular polygons, we're simply going to do this little calculation. It's 360 divided by n, where n stands for the number of sides, or technically vertices, that exist on our shape, because again, sides and vertices should be exactly the same. For example, if we say this is a regular pentagon, the angle of rotation for it would be 360 divided by 5, because there's 5 sides or 5 vertices on our figure, which would give me an angle of rotation of 72 degrees. Again, what that means is if I take this figure and from the center rotate it 72 degrees, it will look exactly as it does right now because it has rotational symmetry. Let's put this information to use. We're going to determine the angle of rotation for this figure. Again, we can identify from the congruent angles and congruent sides that this is a regular polygon. I have 6 sides on this hexagon here, so to find the angle of rotation, I'm just doing 360 divided by that number of sides. That would give me an angle of rotation of 60 degrees. So again, that means if I were to rotate this around the center of this figure, all these vertices would just move over one to the location of the next vertex, and it will look exactly the same as it is now. Again, we're going to be asked to perform this kind of calculation without a figure given, meaning we need to know the names of some of these polygons and how many sides they have. So we have to be able to determine the angle of rotation for a regular octagon. You're expected to know that an octagon has 8 sides. So the angle of rotation would just be doing 360 divided by that number of sides. That would be 45 degrees. So an octagon rotates 45 degrees before it maps onto itself. Now, where rotational symmetry can differ from a line of symmetry is that we can have non-regular shapes that still have rotational symmetry, all right? And so something like this starfish here, right, which is not a regular polygon, can still have rotational symmetry because of the, we could say, or imagine like congruent limbs that our figure has. All right, so this is similar to a pentagon in that it has 5 limbs extending from its center that still gives it rotational symmetry. Every 72 degrees I turn it, one limb moves to the position of the next limb, it still has rotational symmetry. The way that we're gonna be able to find the angle of rotation for these kind of figures is just by dividing by the number of limbs instead of the number of sides, okay? So it's similar to like the number of vertices that our figure has. So again, there's another example of that starfish. It has 5 limbs, so I would do 360 divided by 5 to get 72 degrees. Again, this little flower petal here has 5 petals. So even though there is no line of symmetry, it still has rotational symmetry because I can turn it and it'll still look like this after 72 degrees of rotation. And again, there's just another example of a regular polygon there. 6 sides, so 360 divided by 6. There's 6 things protruding from the center, 6 vertices to give us that angle of rotation. So using this new knowledge, we can find the angle of rotation for these non-regular figures like these. So the example on the left, we can count, we have 1, 2, 3, 4, 5, 6, 7 limbs protruding from the center of that figure. So to find the angle of rotation for that figure, we were just doing 360 divided by 7. 360 divided by 7 would give me about 51.4 degrees. That's rounded to the nearest tenth of rotation for my angle of rotation for that figure. For my second figure, again, we're counting our limbs. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 limbs coming off of that one. If we do 360 divided by 12, we would get 30 degrees as the angle of rotation for that figure. Again, making sure that you have experience here without a figure actually being drawn. This says a 3-leaf clover has congruent leaves. Determine the angle of rotation of the clover. So again, that's just us saying that there are 3 limbs on this thing. They're congruent to each other, so we're assuming that this has rotational symmetry. So we were going to do 360 divided by that number of limbs, or in this case, the number of leaves, and that would give us 120 degrees as the angle of rotation for that flower, that clover. We're going to wrap up our notes here with a very interesting question, right? It's a little tricky. So the ceiling fan has 8 evenly spaced blades. We need to find the angle of rotation required to map the first blade onto the 4th blade. So again, just to make sure that there's clarity in here, when we determined that the angle of rotation on this figure here, this red figure, was 30 degrees, what that means is we could take this limb and rotate it 30 degrees and it would end up exactly where this one is, just one limb adjacent to it after 30 degrees of rotation. What we're going to be doing now is moving a figure more than just 1 over. So the amount of degrees that we're going to be rotating here is going to be more than just that single angle of rotation. But the first thing we need to do is find out what that single angle of rotation is so that we can then add it for all the extra rotations that we do here from the 1st blade to the 4th blade. So with 8 evenly spaced blades, we're just doing 360 divided by 8. And we find that our angle of rotation is 45 degrees. And then we just need to have the critical thinking to understand how many times we would rotate 45 degrees to get from the 1st blade to the 4th blade. All right, so in order to do this, we're gonna draw a little figure here of an 8-bladed ceiling fan. So that would look like so. Would it? 1, 2, 3, 4, 1, 2, 3, 4. That's 8 evenly spaced blades. We'll say that this is the first one, this is the second, this is the third, and this is the 4th. And we've determined to move one blade to the next, one angle of rotation is 45 degrees. So there's 45 degrees to get from 1 to 2. There's another 45 degrees to get from 2 to 3. And there's another 45 degrees to get from 3 to 4. So we're performing 3 angles of rotation, where some people might think to get from 1 to 4 that we're doing 4 angles of rotation. Here's evidence in our figure we're only doing 3. So it's just 45 3 times to give us 135 degrees of rotation to get this blade to where this blade is located. Right, guys, that wraps up our lesson for today. We'll see you in the next one. Bye, guys.